Dear students, today we'll see special purpose PN junction diodes. Now up till now we have seen formation of PN junction, and that PN junction structure was called as a PN junction diode. It is also called as semiconductor diode. And now today we will see some other special purpose PN junction diodes, in which the first one we will see what is a Zener diode and how does Zener diode behave as a voltage regulator. Okay, so here the important things first to understand is the structure of Zener diode, how it is different from the conventional diode, and then we'll see the symbol, and then we will draw a circuit where we are going to use Zener diode as a voltage regulator, and then we will see how the voltage is regulated. As far as the basic definition of Zener diode is concerned, a Zener diode is defined as it is a heavily doped semiconductor device that is designed to operate in the reverse direction. These are very important points of Zener diode. Now, it is heavily doped semiconductor. Now, what does that mean? That means that its structure will be P material and N material only as your PN junction. So, it will be having P material and N material. So, P type of material here, N type of material here. P will be having majority charge carriers as holes. N will be having majority charge carriers as electrons. P will be having minority charge carriers as electrons. N will be having minority charge carriers as holes. And then you will be having a depletion region where you will be having immobile ions. So here you can see negative ions on the P type near the junction, and here you can see positive ions, and because of this you are forming a depletion layer. This is the depletion region, and this depletion region will be having a electric field of its own. So this is your depletion region, and the terminal connected to P type material is anode, and the terminal connected to N type material is cathode. Okay, now here we are saying that Zener diode is heavily doped. This heavily doped means the addition of impurity to the pure semiconductor to make it either P type of or N type semiconductor. So if you add impurity of pentavalent, the pure semiconductor becomes N type semiconductor. If you add impurity of trivalent, the pure semiconductor becomes as P type semiconductor. Now the addition of impurity is more. So heavily doped, doping process. Doping means addition of impurity is more in Zener diode as compared to normal PN junction diode. Now because of this what happens? Because of this what happens is the depletion region will be thin. So here the depletion region width will be thin as compared to normal PN junction, and the electric field of that depletion region will be higher as compared to normal PN junction. So these are the two very important points, and these 2 points come into picture because Zener diode is heavily doped. And second very important thing, we say that we can operate this Zener diode in forward bias also, but its operation in reverse bias is very important, because that feature of Zener diode in reverse bias, where it is going to keep the voltage constant and allow the current to increase at a specific voltage value, that feature will make it useful in application like voltage regulator. Now what is voltage regulator? Voltage regulator is a circuit which will keep the output voltage constant in spite of variation in the input voltage or in spite of variation in the output load. In any of this case, the output voltage should remain constant. So here Zener diode is a device which can be used as a voltage regulator. So these are the things what we are going to see. Now here we have seen the definition first, then we will see the definition of voltage regulator also. Then we will see the feature of Zener diode when it is working in reverse bias, what happens, how the breakdown takes place. And then after that we will go to the circuit which shows that Zener diode is used as a voltage regulator. So here you can see the symbol and the package of Zener diode. So this symbol you can see there is a arrow same like your PN junction diode, and then you are having a bar here. Now only in this bar you can see the bar is bent here and here, and it takes a symbol like Z. So this is a symbol like Z. So this bar is bent. This is the bar which is little bent on the top, and the downside it is resembling like a symbol Z, and that is the difference between your PN junction normal diode and Zener diode. Normal diode symbol you can see like this. This will be your normal diode symbol, but whereas Zener diode symbol is like this. You can have this bar, but this bar is bent here and it is bent here. It takes, okay, so this is your Zener diode. Now Zener diode will have same two type of terminals. One is anode and one is cathode. The terminal towards the p-type semiconductor is anode, and the terminal near the n-type semiconductor is cathode. Now Zener diode practically is available like this. So this is a package which is available practically. So here you can see anode terminal and cathode terminal. This is the strip, and based on this strip you can say the terminal near to the strip is cathode and the terminal away from the strip is anode. So this is your Zener diode. Okay, now this is symbol and structure, and here the structure, again you can say that this structure is nothing but your PN junction as we have seen earlier. So P type of material, N type of material, PN. Okay, so this is anode, this is cathode. Here you are having holes as majority charge carriers, here electrons as majority charge carriers, here electrons as minority charge carriers, here holes as minority charge carriers. There will be a depletion region here. This is negative ions and these are positive ions. So this is your anode terminal and this is your cathode terminal. So this structure, the package and the symbol, all three are shown here for Zener diode. Then how does the Zener diode work in reverse bias? Why it is important? Now we know we have studied the forward biasing and reverse biasing of PN junction diode. Similarly, you can forward bias and reverse bias a Zener diode also. Now a Zener diode operates like a normal diode when it is forward biased. However, when it is connected in reverse bias mode, a small leakage current flows through the diode. As the reverse voltage increases to the predetermined breakdown voltage Vz, for every Zener diode you will be having this voltage specified. What is the breakdown voltage Vz? Because that is the voltage in the reverse bias where the voltage is going to remain constant at that value and the current is going to increase. Okay. So as the reverse voltage increases to the predetermined breakdown voltage Vz, current starts flowing through the diode. The current increases but the voltage remains constant at the breakdown voltage Vz. Now what does this all mean? Okay. Now here you can see what does this all mean. Now first we will see, we have drawn a graph here of x-axis and y-axis. Now in this graph we will take this x as plus volts, and here minus x as minus volts, and then we'll take this y as plus current and this y as minus current. Okay, now here in the forward bias, so for forward bias, how does it look? The circuit will look like this. You will be having a Zener diode here. So this is your Zener diode, say, and if you want to forward bias this Zener diode, the battery connection to the anode terminal should be positive and to the cathode terminal should be negative. So here you will be having negative. So if you have this type of connection, it is forward biased. Now in forward bias condition, it is going to behave same like your normal PN junction diode. That is, if this is your point 0 center point, then you can increase the voltage as 0.1, 0.1, 0.2, 0.3. Okay, so if it is germanium, the forward biasing will take place after 0.3 volt. If it is silicon, it will take place after 0.7 volt. So you can see that the current till 0.3 will be very low. There will be no current flowing, but once you overcome the depletion region, the forward biasing of Zener diode can take place. Okay, it is just like a normal diode. Now, this is not an important feature of Zener diode. The important feature of Zener diode comes when it is reverse bias. So this forward bias is same like your conventional diode. Now, reverse bias, what happens? In the third quadrant, we have shown the reverse bias characteristics. Now, in reverse bias, how you're going to connect the diode? So here you can have the Zener diode. The diode will be connected to the voltage such that the anode terminal is connected to negative of a battery and cathode terminal is connected to positive of a battery, positive, negative. Okay, so this is your reverse voltage. Now this is where we say the diode is reverse bias. Now what happens in reverse bias? Once you initially increase the voltage, say the voltage is 1 volt or 2 volt or 3 volt, okay, 4 volt, 5 volt, 6, okay. So if the breakdown voltage is around 6 volt, so say this is the breakdown voltage, 6 volt. So up till 6 volt, you will be having the minority charge carriers of the diode flowing because of the voltage supply. Like for example, if you show here, you will be having P and N. This will be P-type material. This will be N-type material. You have connecting a reverse bias connection. Now this reverse bias connection for minority charge carriers of P-type. In P-type, the minority charge carriers will be electrons, and in N-type minority charge carriers will be holes. So for this minority charge carriers, this reverse voltage will act as forward bias. So this tend to move here and this tend to move here. So there will be crossover and a small current because of this minority carriers, which is called as leakage current, starts flowing. So this is what we have shown, the small current which is started flowing. So as you increase the reverse voltage, and when the reverse voltage reaches the breakdown voltage of that particular Zener diode, in some diodes it can be 6 volt, in some diodes it can be 12 volts or more according to the manufacturer. Okay, so that will be the breakdown voltage. At that breakdown voltage, what will happen? The electric field of the depletion layer will be more. The electric field will be very high, and because of that, many electrons will break down from their valence orbit. They will come out and become free electrons, and those will constitute a large flow of current, and this type of breakdown will be called as Zener breakdown. So here you can see in the graph, this part of the graph is very important here. Now here you can see this is the breakdown voltage Vz. Say for example, we take Vz is equal to 6 volt. At 6 volt, you can see the current is increasing, but the voltage remains constant. This is a sharp breakdown. So here voltage Vz is equal to 6 volt. As example, we have taken this. So this is going to remain constant, and the current, that is your reverse current minus I, will go on increasing, but the voltage is remaining constant. Now this feature of Zener diode helps to be used in an application like voltage regulator. Now this feature of Zener diode makes it very useful in an application called as voltage regulator, where regulator means it is a circuit which will keep the output voltage constant in spite of variations in input voltage or in spite of variations at the load. Okay, now here Zener diode, if you want to use Zener diode as a voltage regulator, you have to use it in reverse bias condition. Okay, reverse bias condition. Then as I've told you, Zener breakdown is a breakdown phenomena which takes place in Zener diode. Similarly, if you see your normal PN junction diode, in that the reverse breakdown is called as avalanche breakdown. And now in Zener diode, it is called as Zener breakdown. Okay, avalanche breakdown is when the electrons, when they are moving, minority charge carriers, when they're moving, they collide with each other, and in that collision, in that kinetic energy, many minority charge carriers are produced, and that is how the breakdown takes place. That was avalanche breakdown, what is there in normal PN junction. But in Zener diode, the breakdown is called as Zener breakdown, and this is because of the high electric field of the depletion region. Okay, now here you can see the concept of Zener breakdown. When the applied reverse bias voltage reaches closer to the Zener voltage, that is the breakdown voltage, the electric field in the depletion region gets strong enough to pull electrons from the valence band. So many of the valence electrons become free. They will come out from the parent atom. The valence electrons that gain sufficient energy from the strong electric field of the depletion region break free from the parent atom. At the Zener breakdown region, a small increase in the voltage results in the rapid increase of electric current. Now, this is a concept of Zener breakdown which takes in the reverse bias condition. So when we draw the graph of reverse bias condition, the third quadrant, okay, so this is minus current minus voltage. So we can draw this graph like this, and there will be a sharp breakdown. The breakdown happens at a voltage which is Zener voltage. Now this breakdown is your Zener breakdown. This breakdown is your Zener breakdown. Clear? So it happens when the voltage is going to remain constant and the current is going to increase in that. Then we will come to that application of Zener diode as a voltage regulator. So first we will see the definition of voltage regulator. Now whenever we speak about voltage regulator, it is a device or a circuit that maintains a constant DC output voltage irrespective of changes in input voltage or load conditions. Okay, so here whatever there is change in input voltage, if the input voltage increases or decreases, the output voltage has to remain constant. If the load resistance increases or decreases, the output voltage has to remain constant. Okay, so here Zener diode is one device. It is a component which can be used as a voltage regulator. So here is the circuit of Zener diode as a voltage regulator. So here you can see the input we have given as unregulated voltage. Now this is the input what we are going to give here. This is unregulated voltage. So we will name it as input voltage V in. Okay, so it is unregulated, it is not regulated, it is not constant, it is going to vary. And you have a resistance RS here. You have your Zener diode here, which is connected in reverse bias condition. Then you have a load RL here. And here you have the output voltage, which is the regulated voltage, VZ. Okay. Now here, this V in, whatever you are going to apply at the input voltage, is going to produce the current IS. This is say IS, or we can also name it as I in. Okay. So this is your I in. Now this voltage I in or IS, whatever you name it, okay, it is going to flow through RS. Okay, so it is going to develop a voltage across RS. This voltage, will name it as Vs is equal to IS into RS. Okay, now this IS at this junction will break down into two. So here you can see you can have Zener current IZ, and here you can have load current IL. Now Zener current IZ and load current IL. Now this is positive terminal, this is negative terminal. So if you see the connection of Zener diode, this is positive you are connecting, and here you are connecting negative. That means you are connected reverse bias connection. So the Zener is in reverse bias. Okay. Now if the input voltage increases, okay, now if the input voltage, whatever we have shown here, V in, okay, increases, so automatically the input current IS will increase. This will increase automatically when the current is flowing through this resistance. When IS is increasing, this voltage across RS will increase. Okay, and that increased voltage, okay, then in that case there is a current here which is going to flow IL, and this is current which is going to flow IZ. Now the increased current, okay, will be compensated through the Zener diode. It will be IZ will increase and IL will remain constant. So when IL flows here, IL into RL, whatever voltage you get as output voltage, that will be constant. This will be constant, okay, VZ. Now this happens because your Zener diode is allowing more current to flow. Whatever excess current had taken place, whatever excess current was flowing because of the increase in the voltage, that current is going to pass through IZ because your Zener diode is in reverse bias condition. So here reverse bias condition, if you see the graph, If you see the graph, so here this is your current and this is your voltage. So here you can see this is the area where you can increase or decrease the current. So Zener diode, the current flowing through the Zener diode, which is IZ, can be increased or decreased. It will compensate with that increase or decrease, and it will see that the load current remains constant. Similarly, when the input voltage is decreased, when the input voltage is decreased, this current IS, which is occurring because of the input voltage, will also decrease. So when IS is going to decrease, the voltage across RS will also decrease. Now in that case, the current flowing as IL will remain same, but the current flowing as IZ through the Zener diode can decrease, and it will keep the output voltage constant because this current is same. That current multiplied by this resistance will be our output voltage VZ, and that remains constant. That is, the voltage across the Zener diode remains constant. Okay. Now in the first case also, when Vin is increasing, the IZ will increase, but the voltage across Zener diode will remain constant. In the second case, when Vin is decreased, IZ will decrease, but it will see that the voltage across the Zener diode remains constant because it is operating in this area. It is operating in the breakdown area. Okay. So there you can vary the current and keep the voltage constant, and that same constant voltage is your output voltage also. Okay. So automatically the output voltage is remaining constant. A similar thing also can take place with load variation. Even this output load varies. This RL varies. If it is or drawing more current or less current, in that case also the Zener diode will adjust, and it will see that the output voltage remains constant. Okay, so in this way we can have two phenomena here. If the input voltage is varying, it is called as your line regulation, and if the output load is varying, it is called as load regulation. Now in both the cases of variation, the output voltage will remain constant, and this is because of the feature of Zener diode. So this is one more circuit, the same circuit, only thing we have placed that IS in another way. The same circuit is shown here, and here you can have your output voltage, which will remain constant in spite of variation in input voltage or in spite of variation in the load resistor. So Zener diode as voltage regulator, if you want to explain, the unregulated DC voltage is connected to the Zener diode through a series resistance RS, such that the Zener diode is reverse biased. If the input voltage increases, the current through RS and the Zener also increases. This increases the voltage drop across RS without any change in the voltage across the Zener diode. This is because the Zener voltage remains constant in the breakdown region, even though the current through it changes. Similarly, if the input voltage decreases, the current through RS and the Zener diode also decreases. The voltage drop across RS decreases without any change in the voltage across the Zener diode. Thus, any increase or decrease in the input voltage results in an increase or decrease of the voltage drop across RS without any change in the voltage across the Zener diode. Hence, the Zener diode acts as a voltage regulator. Now, here in this explanation, we are speaking only about the change in input voltage. So, if input voltage increases, the output voltage remains constant. If the input voltage decreases, the output voltage remains constant. Now, this as a whole, when there is variation in input voltage and output voltage is remaining constant, it is called as line regulation. So here, that is the concept of line regulation. In this type of regulation, series resistance and the load resistance are fixed. Only input voltage is changing. Output voltage remains the same as long as the input voltage is maintained above a minimum value. Similarly, you can also have load regulation. As I've told you earlier, the load resistance can change. Input voltage will remain constant in that case. The load resistance will change. The load will either draw more current or less current, and that compensation is done by the Zener diode, and it is seen that the output voltage remains constant in spite of load regulation. So here we can have a concept of load regulation also. In this type of regulation, input voltage is fixed and the load resistance is varying. Output voltage remains same as long as the load resistance is maintained above minimum value. So all these features say that your Zener diode in the circuit, to be used as a voltage regulator, it should be first connected in reverse bias condition, and it should be operated in that breakdown region where it is able to keep the reverse voltage constant at a fixed value, and it can see that the current can increase or decrease so that it can compensate with the variations of the input voltage or the output load. Thank you, students.